Hello again, everyone. We're back in the glamorous surroundings of the Brucey Bonus Man Cave. Woohoo! Mask free, because we're both happy with the environment, and we're both fully vaccinated. So, something a bit different from my usual air rifle fare. This is Brucey bonus video on annealing. So it's in particular for anyone who's reloads their own brass, and for the rest of us who are shooters in general with background knowledge of reloading. This is fascinating, trust me. So, over to Bruce. Hi Bruce, good to see you again.
Morning Russ, glad to have you back in the garage again. This time for something a bit different, a bit weird.
Oh, this thing is definitely a bit different. Viewers, we are in proper shooter geek mode now. And if Davey turns up at some point, yeah, it'll be a pair of geek shooters. Awesome. So Bruce, you're a reloader. And a bit of background, basically for those non-reloaders, shooters often reload their own brass because it might save them money, it might not, but they can control far better the cartridges they produce.
And you can manufacture cartridges you simply can't buy commercially.
Yeah.
So I mean you can put a bullet and powder combination together that's not available commercially. So that's one of the main reasons target shooters are the people who do this most, long range shooters.
Yeah.
And dafties like me.
and very, very quickly, basically the upshot is you take centre fire brass, you poke out the primer, and you basically replace the primer and replace the powder, replace the bullet.
That's right.
But along the way, you might have to trim the neck of the cartridge down and so on.
Yep.
But what's annealing, Bruce?
Well, annealing is a process of heat treatment that reduces the stress or stresses inside a material, and it applies to lots of different materials. It's most commonly used to metals, or you can use it on glass, but it's used to reduce the stresses that are built up inside the material either during its manufacture or during its use and the type of service it gets. So as it applies to brass, cartridge brass, when you fire a cartridge, the neck of the cartridge expands. In fact, all of the cartridge expands to fill the space inside the chamber.
Okay.
But most of it returns to its original shape once the pressure in the chamber is dropped. But the actual neck of the cartridge, and to a lesser extent the shoulder of the cartridge, do change their dimensions. So what I'll show you this is a fired cartridge. You can see the primer still in there, and you can see the bump in the middle of the primer to show the cartridge has been fired.
Yep.
So this is a .22 caliber bullet. This is 2250 brass, so it's a .22 caliber cartridge. So if I put, as you can see, the bullet is a loose fit inside the neck. So that shows that the neck of the cartridge has expanded. If I take a piece of brass that's been, that's been resized, in other words, it's been put through a die to constrict the neck again, you can see the bullet doesn't go into the neck of the cartridge. Excellent. And I'll just show you exactly what goes on there, because here's our fired case. Here's our bullet that's quite happily sliding in and out of it.
Okay.
I've got my full length resizing and decapping die here. This is, when I pull the handle, this is going to punch the primer out, and the downstroke and the upstroke will squeeze the neck. So if I run it through okay, so now when I try to put the bullet in the neck of the cartridge, it don't go, because the cartridge neck has now been resized. Now what's happened is that when the cartridge was fired, the neck expanded. When the cartridge has been resized, the neck has been pushed back in again. Both of those operations work the brass and make it harder.
Right.
And if you continue to do that repeatedly, you will eventually get to a situation like this. I don't even know if you'll see that, where the neck of the brass splits.
And so there's the split.
That's a split in the neck.
In the neck of the brass.
And that is a direct result of the brass becoming hard and brittle because of it being fired multiple times and resized multiple times. So if that brass had been annealed and it had been softened between firings and resizing, it would have lasted a lot longer.
Right.
So one of the main reasons for annealing is to extend the life of the brass.
Okay.
The second reason is that this repeated changing of the size of the neck makes the brass more springy. So what we call neck tension, which is how tightly the bullet is held in the neck of the cartridge, for maximum accuracy, you want that neck tension to be consistent.
Okay.
You want every bullet to require the same amount of push to get out the end of the neck of the cartridge. And if the neck tension in the cartridge is the same, then you're going to get more accuracy.
Cool.
And annealing the brass, always bringing it back to the same hardness, means you get more consistent neck tension. If you don't anneal the brass becomes springy, its hardness changes, it's variable. No, you don't really know where it is within its hardness range, so you don't really know how much neck tension you've got. And again, that change in neck tension will have an effect in accuracy, but it's really only at the limits. I mean, if you're shooting short range, it's not going to make any difference. Target shooters and long range shooters are the people who really benefit most from annealing brass.
Okay.
For most ordinary everyday shooters, guys that go deer stalking, you wouldn't bother.
Right.
But if you're a long range shooter, target shooter, where you're trying to control every variable to minimise things that cause the bullet not to go where you want it to go, then annealing is definitely something that's worth considering.
And those people are more likely to be reloaders anyway.
Yes.
Yeah.
Yes. I mean, target shooters are shooting hundreds and hundreds of rounds each year. Obviously, for them, it is more sensible to reload brass than to continue, because if they're continually buying commercially bought brass, they don't know exactly what they're getting. Mm-hmm. They're then subject to the variabilities of the manufacturer
And they have
process.
to test every batch and so on.
Well, you'd have to test every one, which is a bit pointless. But if you know your brass and you're annealing it, so you know you've got the same product every time, and it's also kind of fire form to the chamber of your rifle, it reduces the variables and gives you a little bit more control. There's also an element of confidence in this as well. If you feel confident in your brass, then fair enough. So that's basically kind of covers what annealing is, why we should do it on cartridge brass, and who would be doing it, I would say. So how do we actually perform annealing? As I said, annealing is a heat treatment process. So we've got to heat the brass to a point where we can allow the crystal structure within the brass to change from its high stress state back to its relaxed state that it would be when the brass is fully annealed and as new. So that involves heating the brass up to a temperature somewhere between 425 and 650 degrees centigrade. And I'm not going to do conversions into Fahrenheit because that's a muppet temperature range. So I'm sorry, we're sticking with centigrade. If you really want to be arsehole, I'll go to absolute, but never mind. So we heat the brass up, and it's normally we hold the brass at a temperature for a given time. That's basically the process. You heat the brass up. If you're in the lower end of that temperature range, you've got to hold it there for a longer time. If you're up at the top end of that temperature range, the time involved becomes less. It's almost like you have to put a certain amount of energy into the cartridge. So high temperature, short time, low temperature, longer time. But exactly where that is, nobody really knows.
Oh, right, okay.
Okay, and that's kind of what we're going to come on to, is say,
Right.
How do we know when we've done this right?
Yes.
The other thing that's important to note that is when we anneal the brass, we only want to anneal the neck and the shoulder.
Right.
We don't want to anneal all the way down the body of the brass. We don't want this area down the body to become soft, because what can happen then is that when the cartridge is fired, you can eventually cause the cartridge to part down here.
Okay.
And a body failure when you fire a cartridge is not good news.
Okay.
Because one of the reasons being that when you fire a cartridge, the expanding gas causes the case to expand and seal against the chamber of the rifle.
Right.
So that none of the gases can go back down out towards the shooter. That forms a seal. If your brass here is weakened and that breaks, you've got a huge burst of gas coming back out through the bolt. Right in your face. Not a good idea.
No.
So we definitely don't want to soften the brass down in the body.
Okay.
Otherwise we run the risk of having a major failure down here. We only want to heat the neck and the shoulder region.
Okay.
And get them softened down. Okay, so we've said that annealing is a process by which we have to heat the brass to get this brass to become softer. So how do we do the heating? As far as annealing brass cartridge cases are concerned, there are three commonly used methods. The first one is the cheapest one, and the one that is probably most common is using something like a gas torch, something like this.
Yeah.
Okay,
Yeah.
And there are, if you go on YouTube, you'll see plenty of videos where they have brass torches mounted, one or two brass torches mounted on some sort of table, where the brass cartridges then move round and move into and out of the gas flame.
Okay.
The real cheapskates use something like one of these cartridge holders. You stick the brass into the cartridge holder. If I can get you tighten it up, you switch on the gas torch and you rotate the cartridge.
Okay.
It works, but it's not exactly a well-controlled process.
No.
So
there's a lot of variables there.
A lot of variables there. So that's one method, gas. The second method is this, what we call molten salt method, which is basically you buy potassium nitrate and sodium nitrite powder in powder form, and you buy one of these little melting pots and put the powder in, heat, bring it up to about 500 degrees centigrade, at which point it's melted.
Right.
So it's now molten salt, and you simply dip the cartridge into the molten salt. And according to the people who recommend this method, you hold the cartridge in so that the neck of the cartridge is under the molten salt for about 5 seconds, and that anneals it.
Yeah.
I looked at this method and I thought, oh, that's quite interesting. It's quite simple, quite straightforward. I wasn't keen on having 500 degree molten salt in the garage, and I'm not really happy about having an open flame in the garage either. But
No.
so that I did a bit more research, and I found a really interesting paper by a company called Annealing Made Perfect, who Annealing Made Perfect are a New Zealand company who build an induction annealing machine called the AMP machine, and it's the Rolls Royce of annealing machines. Okay, so you could argue that they've got a dog in the fight, but they've published so much good research online, a lot of laboratory stuff, a lot of hardness tests, really brilliant, and they've done tests on salt annealing.
Brilliant.
And what they have shown is that basically it doesn't work.
Oh, right.
That it looks like it works, because when the brass comes out of the annealing bath, the molten bath, it looks the same as a piece of brass that's been properly annealed.
So the surface
colour change, when you see annealed brass like new, this is brand new Lapua brass, okay, and you can see there's clearly a colour change.
Oh, there we go. So there we can see just above my thumbnail, you can see the colour change from there up to the end of the brass case.
And that colour change is what a lot of people use to decide whether something's been annealed or not. Okay?
Right.
The problem with that is that with this salt bath annealing method, you can put the cartridge into the molten salt, leave it for 5 seconds, pull it out, and it looks like that.
Yes.
But when you hardness test it, it's still hard.
Right.
So that...
It hasn't been softened.
It hasn't softened. So that was kind of a major deal for me in deciding that I'm not going to go down the salt bath method.
Yeah.
The third method is induction heating, which is what we've got here. And because I'm a kind of electrics and electronics guy, I was obviously attracted to induction heating anyway.
Yeah.
But I think it's the most controllable of all the three methods. Low risk, there's no molten salt, there's no open flames going around.
Yeah.
So for me, induction heating was the way to go, and this is what I've built, is an induction heating annealing unit.
We have a Brucey bonus induction heating and annealing machine, and one thing regarding safety, you can always plug this machine into the mains into a circuit breaker if you're worried about.
It's plugged in here. It's through my earth leakage circuit breaker in the garage.
Okay.
If it's too much power, it'll trip the breaker.
Okay.
And even the main power supply that it runs from has got overload built into it. If I was to try and put a chunk of steel in there,
right,
which would draw a huge amount more power than brass does, the power supply would simply shut down. It wouldn't do it.
Brilliant. So we've got safety built in.
So we've got safety built in. And the fact we're not running a lot of power here. We're running much less power than I originally thought we would use. So I mean, I've over-designed it in terms of protection from overheating and so on. So
yeah,
it's. I mean, I can demonstrate. I could stick my finger in there when this thing's running, and because my finger's not metallic or magnetic, it will not get hot.
Right. Don't put your finger in there with a wedding ring on it.
No, not with the way that would not be good.
No. Okay.
But that would be okay.
Fascinating.
So this is basic what we're coming to now. This is the induction annealing machine. So I'll switch it on. You know, it runs on a timed cycle, and when you switch on, it's going through its cycle at the moment. And once it's finished its cycle, it'll shut down and be ready to start again. Let me step back and let me kind of explain what happens here.
Okay.
We've got a power supply down here that's turning mains voltage into about 36 volts DC.
Right.
And when I hit the go button, the start button, there's a relay that allows that 36 volts to flow into this thing at the side here, which is called the zero voltage switch. It's an electronic circuit. This is like a small version of what's in there. That's a 1 kilowatt switch. This is that one in there is a 2 kilowatt switch, but they both do the same thing.
Okay.
They basically convert direct current into high frequency alternating current. And what's coming out of here is about 100 kilohertz. That's just the frequency at which the current is flowing through the coil. Okay, so the load, you might say, is this coil, which is made up of a piece of 5mm copper tube. Okay. So the coil is formed from a copper tube. This is insulation material so that the turns don't touch each other and create short circuits. It's a copper tube because I've also got a tank of water up here and a pump, and I'm pumping water through that coil. Because I didn't know how much heat I was going to have to deal with here, I decided to go with a tube rather than a solid copper wire, so that I could pump water through the tube for cooling. As it turned out, I've got heaps and heaps of cooling. You can also hear a couple of fans going that are blowing coal there down the top of the zero voltage switch and out through the side of the case.
Right, okay.
So we've got bags of cooling, plus we're not in the warmest place in the world. But I was concerned that we might have issues with the thing overheating. But as it turns out, we don't have a problem. So this high frequency alternating current flows through this coil, which produces a magnetic field in this direction. But it's reversing. For half the cycle it's going down the way, or half the cycle is going up the way. So you've got this rapidly changing magnetic field inside the coil. So when you put a piece of brass in, right, what happens is that although brass is not magnetic, it is an electrical conductor.
Yep.
And because that brass, that electrical conductor, is exposed to magnetic field, a changing magnetic field, electric currents are induced inside the brass. They're called eddy currents. So those currents, because in magnetics and electrics, if you've got an electric current going one way, the magnetic field's always at 90 degrees. If you've got a magnetic field in one way, the electric current's always going to be at 90 degrees. So we've got electric current flowing this way, which gives us a magnetic field going that way. The magnetic field going that way induces an electric current around the way. So in other words, we've got a circular magnetic current flowing around inside the brass. And that current is high, maybe it'll be hundreds of amps. And the resistance of the brass, combined with the electric current flowing around it, is what makes it get hot. In the same way that the current flowing through the heating element of your electric kettle makes it get hot, well, the electric current flowing through the brass and its resistance is what makes the brass get hot.
Brilliant. Okay.
So when we turn on the power, the current flows through the coil, the brass gets hot. When it times out, the electric current switches off, this little flipper opens under here and the cartridge drops down out of the way.
Brilliant.
So I will demonstrate.
Oh yes, please.
So we'll start with a nice shiny piece of brass.
Yep.
Okay, this has been tumbled, so there are no colour markings on this at all. This is shiny, it's the same all the way up, right?
Yeah.
So we'll stick it in there and I'll just hit start. I figured out 8 seconds is the time it takes. Now,
oh, I can smell the heat.
you can smell the heat. What I'll do is I'll get your pliers. And you can see the classic colour change.
Yeah. There we go. Yes. See the colour change.
I will do another one.
Okay.
We'll do another one. And this time we'll drop it into water and it'll cool quicker.
Does that Is that detrimental?
No, it doesn't. Not with brass. It can do with some materials, but not with brass. Brass is what's called a single phase alloy. It doesn't suffer from cracking when you cool it too quickly.
Okay.
It just cools it quickly.
Okay, brilliant.
There was actually, I was concerned when I started this that because this is quite a long cycle time compared to some annealers. Some annealers are running 2 and 3 seconds to do 2 brass. This is about 8 seconds,
Right.
and I'll explain why that is. I was a little bit worried that the heat would travel down the body of the case and overheat the body, which is what we were speaking of. One of the ideas was okay, if when the cycle's finished, we'll just dunk it straight into water and it'll stop it. I would prefer not to, because it then becomes an extra step in the process. I've then got to dry the brass.
Yes.
I've since done some tests and found out I can just drop it and allow it into the metal tin and let air cool.
Yeah.
What I did was I took a piece of brass, and chopped the head off the case,
Yeah.
annealed it, measured the hardness before, top and bottom,
Yeah.
annealed it, measured the hardness afterwards. The
Yeah.
top end was annealed, the bottom there was no change in the hardness. So,
Brilliant.
and that was air cooled. So I was convinced that I was not putting brass down here at risk by air cooling.
Yeah.
But for the purpose of letting us get our hands in a cartridge quickly once it's annealed, I'll dunk this one in the water so you can
Okay.
hold it and put it where you want in front of the camera.
Okay. Boys' toys.
So that's cool now. It's instantaneous.
So there we go. There's the colour change.
But that's
That-
what the legal people will call prima facie evidence. but it's not proof.
No.
It's not proof.
It's not proof that the annealing works.
No. No.
You know something's
only-
happened.
We know something's happened. So one of the questions I had when I was researching this was, how do we know it's annealed?
Yeah.
And what I found by watching various videos is there was sort of 3 different ways. One was to observe, like if you use the flame method, you basically go until you start to see the neck of the brass turning cherry red.
Right.
Similarly, with the induction annealer, if you look down at the cartridge case
Yeah.
when it's heating up, you
Yeah.
can see it changing colour. The problem with that is if it's a sunny day or you've got a lot of light in the room, you get a different answer from if it's a darkened room. Because if it's a dark room, you see the cherry red more easily than
Yeah.
you would if it's a bright sunny day or if you've got a light. So there's no consistency there. So when I asked the question, how do I know if it's annealed? One answer was, look for the brass getting red hot.
Yeah.
Okay. Second one was this change in colour here. If you start out with a shiny cartridge and you look at the cartridge when it's being annealed, you can see that surface texture change from shiny to matte.
Right.
You can actually see that happening.
Right.
And we can maybe try and do that with the video camera and watch
Okay.
it.
Just filming the annealing machine in action. This is 8 seconds.
Cartridge is in. Press the start button. It's now annealing. And when it gets to 8 seconds, the cartridge will drop down. There you go. You can see the cartridge lying in the bottom of there.
Yep, and
You can see that change in colour at the neck of the cartridge.
yep, you can
To
definitely
indicate
see the
that it's
colour
annealed.
change. Right, that's recording.
Okay, let's try it. Did you see that colour change?
Yes. Yes, that was perfect because there was a wisp of smoke and a colour change.
That's fine,
Excellent.
that's what I wanted. And the third method, of course, was this obvious colour change here.
Yeah.
Those were the 3 methods, right? But nobody was measuring hardness.
And the hardness is changing
hard-
the hardness is the whole purpose.
The whole purpose of annealing is to reduce the hardness, but nobody was measuring hardness. Now, the reason they weren't was because hardness testers, the type of hardness testers that are used to measure the hardness of the brass, are big, heavy, and expensive.
Yeah.
Right? I mean, even the simplest Vickers hardness tester is going to weigh about 30-40 kilos, is going to need to be sitting on a bench, and it's going to cost you'll get no change out of £2,000.
Right.
Okay? They're also difficult to use and really slow because you've got to apply your load, then you've got a microscope you have to look through. You have to look through the microscope and adjust everything to measure the diagonal on one diagonal. Then you've got to turn the microscope around 90 degrees. I mean, there's videos showing this done, and it's a pain in the backside. So I kind of, when I kind of looked at all this, I thought, there's no point in doing this, because if I can't be sure about whether or not the brass is annealed, what's the point?
Yeah.
You know? So, because I've done quite a bit of hardness testing in my work life, I know a fair bit about hardness testing and how to do it and what the different scales are and the rest of it. And I had never come across a hardness tester that came anywhere close to doing what I needed to do for a sensible price.
Yeah.
You know? Then I started seeing things called a Webster hardness tester. One of these things, which I'd never seen before, right?
Brilliant.
And I thought, oh, this looks interesting. And the price, it was still expensive. You know, okay, it was still a couple of £100, and the prices were all over the place. And I just happened to go into Amazon UK one day and pump in Webster hardness tester, and not pop this thing, £36.
Oh,
So I thought, I'll have that.
yeah, yeah.
So, unfortunately, I've never seen it again for £36. If I go on Amazon UK now, they're unavailable. And if I search the internet, the cheapest I can find them for is about 200.
Oh,
So I maybe got a bit lucky there.
yes. Well done.
But-
well
but-
done, Bruce, and thank you, Amazon.
And even at £36, it was a bit of a punt. I didn't know if it was going to work on. These things are designed to work on thin materials.
Yeah.
And in fact, when you buy it, you get a couple of pieces of thin aluminium, as calibration pieces that allow
Right.
you to calibrate the hardness test.
Okay.
So I knew that it would work in aluminium. It came with a good manual, it came with good tools. I had to modify it to make it work in cartridge brass.
So-
The anvil was too big to let the brass go in it, so I had the anvil sanded down, or belt sanded down, leaving the top surface as it originally was.
So now this gadget here that holds the brass is now slim enough.
It'll take 2.2. It won't take 2.0 or 1.7. 2. I then had to also modify this bit here
Okay.
to allow the cartridge.
There's a tip that comes out there. There we go. Right in the centre of this bit that projects outwards is a tiny little probe that then presses into the metal and displays on here.
So if you pull it now down hard, it should go to 20.
Yep, straight up to 20.
So with my now modified hardness tester, I'm now able to measure the hardness of the brass at the neck, about 3mm in from the end of the neck, which is just the perfect position.
Right.
So I can now easily measure the hardness of the brass before it's annealed and after it's annealed.
Yep.
So now I've got confidence that I am actually annealing the brass.
And for thoroughness, you wanted to check if your measurements were right.
Yes, exactly. This machine gives me numbers, what I felt were sensible numbers. However, it measures on its own unique hardness scale called HW, Hardness Webster. And all the hardness values I had, and most of them, all of those came from either internet searches on brass or amp annealing, were given numbers in what we call Vickers hardness, which are two different hardness scales. And I know from my work life that converting from one hardness scale to another is always problematical.
Right.
Because the actual materials you're testing and the method are never exactly the same. What I needed was to be able to validate what I was measuring was consistent with what the hardnesses were in Vickers hardness, which were like my reference values, the values that the amp annealing have produced,
Yep.
of round about 100 Vickers for virgin brass that's never been fired.
Yep.
So what I did was I found a local materials testing laboratory called Element Materials Laboratory, and I gave them 12 pieces of brass. This is all Lapua,
Yep.
22250.
Okay.
I gave them 4 pieces brand new unfired,
Yep.
4 pieces that had been fired once and resized,
Okay.
and 4 pieces that had been fired multiple times and resized. I don't know how many, they'll probably be different.
Yep.
And I asked them to test each case 4 times at the neck, 3mm in from the end,
Okay.
at 90 degrees apart.
Okay.
Okay, so that gave me 16 values for this, 16 values for this, and 16 values for this.
Yep. Cool.
And the results came back, and the agreement with the amp values were extremely good.
Excellent.
The virgin brass values were very, very consistent with what amp were finding. Element were coming back with the new brass coming out at Vickers between 98 and 103,
Okay.
and amp were coming at, they're saying between 90 and 105. So I mean, that's good agreement.
Yep.
The other thing was that the 3 different sample groups broke into 3 clear hardness bands.
Brilliant.
This was soft, this was significantly harder, and this was a little bit harder still.
So they were nicely distinct.
Yeah, there were 3 distinct bands. There's a big gap between the new and the ones fired, and a somewhat smaller gap between the ones fired and the multiple fired, but again, still a distinct gap. Although my numbers don't tally up when converted to Vickers with the Vickers numbers, I also can see 3 distinct hardness bands with my tester.
Yeah.
With the Webster hardness tester, new brass is coming out at 12 to 14, ones fired coming out at 15, 16, and the multiple fires coming out at 17, 18. Although that sounds close, it's easy to read that scale,
Yeah.
and they're consistent. So I'm happy that my hardness tester does a good job of telling me when the brass is annealed.
Yeah.
And I can show you that. Right, this is a piece of fired brass. You see that 17?
Yep.
Okay. So,
Yep.
right, let's anneal it.
Talk amongst yourselves for 8 seconds.
Loves it, yeah.
I love that machine.
You know something? It took me longer to figure this bit out than anything else.
There we go. Yep. Oh, 13. 12 and a half, in fact. So that is clearly
Softer.
softer.
This is one of my reference pieces that was tested by Element Materials Laboratory, which is new brass,
Yep. 13. Excellent.
same as new. So I think I've just proved fairly clearly that
Yep.
the brass started out hard,
Yep.
17, 18.
Yep.
We've annealed it and we've brought it back to the same value as my brand new brass, which has been tested by the laboratory.
Yep.
So I think that kind of proves,
Excellent.
validates the method.
Yes, absolutely.
I think that validates the method. So I'm now confident that I can take brass and anneal it and be confident that it is properly annealed.
Excellent.
So once I found that, and I was happy to proceed with the project once I got my hands on this and I'd done a bit of testing, that I could be sure that I was doing it correctly.
Brilliant. So, what happens if the brass is not correctly annealed?
If it had come out of there and it was still hard, I'd just up the time.
Right.
I'd increase the time. I can also modify the time settings here to the nearest hundredth of a second. I mean, but I normally maybe a tenth of a second. And that's when I started with new brass. Like if Davey comes in with the 6.5, I'll probably set that at about 4 seconds. I'll test it beforehand,
Yeah.
set it at 4 seconds, run it at 4, see how the hardness is after 4. It probably won't have reduced. Bump it up to 5, try it again. And then eventually we'll get to a point where we get it down to the required softness. So if you don't get it soft enough, that's what you do. You just bump up the time. If you put it in for too long, that's what happens. If you leave it in for too long, you melt the brass.
Ah, so these 2 cartridges are examples that you've literally melted in your own machine.
Yeah. In fact, the big one, this was 22-250, which is what I've done most of my work with. But one of my pals who shoots a bigger cartridge, 3006, which is a
Right.
famous American cartridge.
Yeah.
30 caliber, developed in 1906,
Yeah.
classic cartridge. And he gave me some of these, and I'm thinking, well, that's a bigger cartridge than 22-250. I mean, just look at the size. I mean, there's more brass in there.
Yeah.
But clearly, that's going to take longer to anneal.
Yeah.
So I had it set up for 8 seconds, which was the time for the 22-250. Stuck that in there, hit 8 seconds, and after 7 seconds it melted. And I still don't understand why. So I had to back it off to 6 seconds
Right.
before I could get it to anneal properly,
Without destroying the cartridge.
without destroying the cartridge, and to get it down to what it should be.
Yeah.
So that's what I mean. You've got
Well, maybe one of our viewers will be a shooter and enough of
Well,
a science geek
maybe.
that they'll either have an answer
Maybe.
or they'll do some research and come up with an answer.
I don't know, but it was an interesting thing to happen.
You have an awesome machine here that not only does some highly scientific stuff, it goes splash at the end.
What I've found is that you can actually over anneal to the point where the brass is softer than it is new without melting it.
Right.
I've had some cartridges down to that hardness test are down to 9,
Right.
and it's not melted. And what I did notice with them was when I then reloaded them, when you put the bullet into the case, normally when you're inserting the bullet, you use a different die, but basically it's still the same thing. You're basically pulling the handle down, and you can feel resistance as the bullet is pressed into the neck of the case.
Yeah.
But with those that were at like 9 hardness, you hardly felt any resistance to the bullet going in. So the brass was obviously very soft, and it was allowing the bullet to slide in. Now, whether that's good or bad, I don't know.
Well, you definitely don't want the bullet too far in.
No, but although I have read about some target shooters who really want as little neck tension as possible.
Right.
Almost to the point that they single load the bullets because they don't want the bullets in a magazine getting pushed in by the bolt.
Oh, right.
Or because it might make the bullet move inside the neck of the case.
Right.
They're very careful about loading the bullet loading the cartridge so that the bullet doesn't move.
Yeah.
So they must have minimal neck tension.
Right.
But that's not practical for most people.
But
you can't have the bullet moving backwards and forwards in the case.
No, but if one of those people wanted minimum neck tension, then
you could probably do it.
this machine could do it.
Probably could, yeah. Well, like tuning with the time, we can do it. Yes, sir. 7.93 seconds. That's what you need.
Awesome.
Most of the work I've done with the annealer has been on Lapua brass, because that's what mostly I have. But I do have some PPU brass. PPU is made in Serbia, and generally PPU ammunition is the cheapest ammunition you can buy. And I bought some 22-250 PPU ammunition. I used it, and this is the brass from it, which has been full length resized, so fired once, full length resized. So what I'm going to do is I'm going to show you this once fired and resized PPU brass.
Yep.
It's about 17
on the hardness meter.
17 on the hardness meter, right? We'll take that bit of brass, we'll stick it in the annealer, switch the annealer on. And we're going to have to wait a little minute until it cools down because I'm only air cooling here.
Right.
Right, that's it annealed. In fact, I'll stick it in a bucket of water just to cool it down more quickly so I can handle it.
A little fizz there when that went in.
Fizz now went in. And we'll see what we get.
Let's line that up.
I lined up on the shoulder.
Okay.
Can you read it?
Yep. So 13.
So that's knocked it down from 17.5 to 13. 13 is what new Lapua brass is.
Mm-hmm.
So that is now back to being the same as new Lapua brass, from being very hard at 17.5.
Right.
So this is now very, very good usable brass.
Excellent. Thanks, Bruce. You've developed this, so it's an awesome gadget to anneal your own brass, which assists with your reloading and prolongs the lifespan of your brass. Where do you go from here?
Well, what I've decided to do is, as a friend of mine, the guy you know as well, Mike McClellan out at Annealing Field Sports, and what we're going to do is Mike's going to advertise brass annealing as a service.
Right, okay.
People who want to get a brass anneal can give it to Mike, and I'll do the annealing.
Right, okay.
And what I'm proposing is that, let's say somebody gives me 100 cases, I will hardness test, random 10% before and after. Test it before, anneal it, test it after. That's after having established the correct annealing time for that particular type of brass. But once I've established that, then I'll do 10%, and I'll basically report back and say, right, I can now confirm that all your brass is now down at 12, 15 or whatever.
Yeah, brilliant.
It's now fully annealed. So,
okay, so shooters who are watching this video, if they want to anneal their brass to extend the life of it, they can now.
If they contact Mike McClellan at Annealing Field Sports, he'll be happy to take the brass off their hands, and either I'll go out to his and do it there, or he'll give it to me and I'll do it here, and we'll get you your brass back. And
we'll put the contact details for Annealing Field Sports down below here in the description.
Yep.
Brilliant. Well, thank you, Bruce.
So, I think that's it.
Excellent. That's a hell of a gadget. The only thing I can think of, an improvement, in inverted commas, is this PC tower you've used. I've seen gamers customise gaming machines, and they've got coloured water bubbling through tubes in the side, and they've got various neon flashy lights in the side.
Well, I could change the water to coloured antifreeze liquid, and that would give me pink liquid flowing at the back here.
So if you wanted the bling version of your annealer, you could do it.
Well, the other thing this has got that I've not seen anywhere else, it's got this thing here, which basically tells me the power, the voltage coming out of the power supply, the current that is being drawn, and the power that's actually being consumed.
Right.
So it might be interesting to see how how little electric power we are actually using. So at the moment, the thing's not switched on, we're not drawing any power. What I'll do is I'll run a cycle with nothing in the coil. That'll let you see how much power the coil is consuming without any. So, and that number there, that power number, it'll rise as the cycle proceeds, but it's going to finish up at about 410 watts peak.
Okay.
So when I put a cartridge in, the power's going to be higher.
Yeah.
But it's not that much higher. So watch again. Just under 500 watts. So we're only putting about 90 watts of power. The other little thing, obviously you've got different cases will be different sizes, and you also always want the neck of the case to be in the same place relative to the coil. So it's basically a bolt and a washer. We're cutting it so that sits in there. This table moves up and down, so that you can accommodate
larger
so for
cartridges.
example, if I put that cartridge in there, I just want to bring up the table until the neck of the cartridge hits the bolt. Then I know, and I tighten it off there. Then I know that it's not critical, but then I know that the neck of the cartridge is in the same place each time.
Okay.
That's all right.
Okay.
Because obviously, with that, if I put the 22250 in there, the neck of the cartridge would be away down here.
Yeah.
So
you've got adjustment for different cartridges.
Adjustment for different cartridges.
And your handheld hardness tester will cope on anything from 2.2.
Anything 2.2 caliber and up.
It's brilliant, Bruce. Thank you for inviting us in to see your new gadget. It's well impressive, and I love the kaplunk factor in it as well. But you've basically created an awesome little piece of kit here, or awesome big piece of kit. As you've talked us through, you've proved the methodology. So your annealing process is spot on.
Yeah, I think it's now, I understand it, and I've now got a controllable method of reproducing consistently the brass with the hardness that's needed. I can get it back to pretty much any hardness I want.
Yeah, brilliant.
So I'm happy with how it's worked out. I must admit, I'm quite pleased with how it's worked out.
Excellent. Yay, Boffin's happy.
Yeah,
brilliant.
And I suppose, and you always ask me, how much did it cost? Right, let me tell you, total cost of parts, 250 quid.
Okay.
In about a fortnight of my time.
That's a lot, which is worth a lot more than 250 quid.
A lot of time just sitting there looking at things and thinking about it, and took a long time to build it, but it was good. I enjoyed it. It was a good process.
Excellent. And you've got a gadget that people can make use of, a service,
that's right,
if they wish.
Yep.
Awesome. Thanks, Bruce.
No problem, Russ. Thank you.